Hi, everybody, and welcome to 10-4, Multiple Regressions. Key concepts. This section presents methods for analyzing a linear relationship with more than two variables. We focus on these two key elements: finding the multiple regression equation and using the value of the adjusted R-squared and the p-value as measures of how well the multiple regression equation fits the sample data. This section emphasizes the use and interpretation of results from StatCrunch. When we were doing simple linear, we had an X and a Y. Now we have a Y, and we could have multiple X values. A multiple regression equation expresses a linear relationship between a response variable, which is Y, and two or more predictor variables. They're all called X. It's X sub 1, X sub 2, to differentiate the different X values. Don't get too worried about the notation. The general form of a multiple regression equation obtained from sample data is this equation. This is still the intercept. This is normally our slope and our X value, but here we have a different slope with a different X value. We don't know how many different X values we are going to use. That's why it's M sub K. I might use 1, I might use 2, I might use 5. I have data, age, gender, weights, heights, waist, arm circumference, BMI, which is body mass index. Click the Stat tab at the top of the screen, click on regression, and go to multilinear. Our Y value, our output is BMI. And we want to use age, gender, weight, height, and waist. Hit compute. We have this information. When I selected the Y variable, we entered that. That's the dependent variable. And then we click all the X values. To get more than one, you hold the control key down, and then you select all the variables that you want. Then we have R squared, and we have our adjusted R squared. For this, they're very similar. Our p-value for the entire regression is right here. It's very small. Gender is not that great of an indicator. Age is also not great. And waist size is not great. Let's see what happens if we take those away. Our p-value changes and our R-squared value changes. I'm going to leave my BMI the same, and I'm going to use weight, height, waist. Hit compute. Our R-squared and our adjusted R-squared doesn't seem to have changed much. Our p-value is similar. Everything looks good except waist is not necessarily contributing that much. It's actually got a higher p-value than we would like. We want to take that away and see if anything changes. We want to use the minimum number of variables. That's always the best. It looks like our R squared is still up there. Our p-value is still good. And all our p-values here are nice. This looks good. If I want to find the BMI using height and weight, it looks like I could get a very good estimate. It also looks like the data is going to fit this equation very well, which means that I could make some predictions. The intercepts and coefficients of the X variables and the multiple regression equation will also be provided. This is the multiple regression equation. These are the coefficients. This would be the constant. This would be our X1. This would be the slope in front of the X1, and this would be the slope in front of the X2. Finding a multiple regression equation, our objective. Use sample matched data from 3 or more variables to find a multiple regression equation that is useful for predicting values of the response variable Y. Our notation: K is the number of predictor variables, also called independent variables or X variables. N is the sample size. Y hat is a multiple regression equation found from sample data. And Y itself is the multiple regression equation for the population. Y hat is the predicted value of Y. It's an estimate. It's not always precise. Our requirements: for any specific set of X values, the regression equation is associated with a random error, often denoted by epsilon. We assume that such errors are normally distributed with a mean of 0 and a standard deviation of sigma, and that the random errors are independent. I have height, waist circumference, and weights from a sample of 153 males. And I want to find the multiple regression equation from which the response variable Y is the weight of a male and the predictor variables are height and waist circumference. I go stat, regression, multilinear. The response variable is the weight. I want height. I'm holding down the control button, and waist to be my predictor variables, my X variables. I hit compute. Using StatCrunch with the sample data, we obtain these results. Y hat equals -149 plus 0.679 times the height plus 1.01 times the waist. It's nice the way they write it here, because if you just write X1, X2, you may forget what those are. But if you write the actual name of the variable, you won't forget. Our p-value is small. Our r squared and our adjusted r squared are very similar. And all our p-values are nice. We never really worry about the p-value for the intercept. Follow up to example number 1. If a multiple regression equation fits the sample data well, it can be used for predictions. For example, if we determine that the multiple regression equation in example 1 is suitable for predictions, we can use the height and waist circumference of a male to predict his weight. But how do we determine whether the multiple regression equation fits the sample data well? There are two very helpful tools, and those are the adjusted R squared and the p-value. Take note, this is very important. We're always going to be looking for our adjusted R squared value and our p-value. We're not going to be using this equation. I put it in here just like always so that you understand where it's coming from. N is the sample size, and K is the number of predictor variables. Our sample size and predictor variables is going to change our R squared value. R squared denotes the multiple coefficient of determination. Remember, our coefficient of determination was R squared, which is a measure of how well the multiple regression equation fits the sample data. A perfect fit would be R squared equals 1, and a very good fit results in a value near 1. A very poor result would be R squared is close to 0. The value of R squared equals 0.878 in the StatCrunch display, and our adjusted is 0.867 or 0.878. If the value of R squared is this, that means that 87.8% of the variation in weights of males can be explained by their heights and waist circumference. This is a good determinant for how we could estimate someone's weight. However, the multiple coefficient of determination R squared has a serious flaw. As more variables are included, R squared increases. R squared could remain the same, but it usually increases. The largest R squared is obtained by simply including all of the available variables. We would think that the bigger R squared is, the better, but that's not necessarily true. That's why we're looking at the adjusted R squared. The largest R squared is obtained by simply including all of the available variables, but the best multiple regression equation does not necessarily use all of the variables. Because of that flaw, it is better to use the adjusted coefficient of determination. That takes into account the number of variables and the sample size. Again, the more variables you add, the larger the R squared gets, but that doesn't mean it's a better equation. The definition, the adjusted coefficient of determination is the multiple coefficient of determination R squared modified to account for the number of variables and the sample size. Guidelines for finding the best multiple regression equation. Number 1, use common sense and practical considerations to include or exclude variables. For example, in the one we just did, if we also had their shoe size, that probably doesn't affect their weight. It wouldn't be something we would include in the multiple regression equation because it doesn't really make sense to include their shoe size. They use common sense. Again, consider the p-value. Consider equations with high values of adjusted R squared and try to include only a few variables. This is very important because the less variables that you can include and still have a good regression equation, the better. Instead of including almost every available variable, try to include relatively few predictor variables. Use these guidelines. The less, the better. We want to use all the variables that actually will help us to get a better prediction, but we don't want to use more than what we need. We want to use the least amount of variables that gives us the best information. Select an equation having a value of adjusted R squared with the following property. If an additional predictor variable is included, the value of adjusted R squared does not increase very much. If that happens, we don't want to add that predictor. For a particular number of predictor x variables, select the equation with the largest value of adjusted R squared. In excluding predictor x variables that don't have much of an effect on the response variable y, it might be helpful to find the linear correlation coefficient R for each pair of variables being considered. If two predictor values have a very high linear correlation coefficient, which is called the multicollinearity, there is no need to include both of them, and we should exclude the variable with the lower value of the adjusted R squared. Our second example, data set 2, foot and height, includes the age, foot length, shoe print length, shoe size, and height for each of 40 different subjects. Using sample data, find the regression equation that is best for predicting height. Is the best regression equation a good equation for predicting height? Using the response variable of height and the possible predictor variables of age, foot length, shoe print length, and shoe size, there are 15 different possible combinations of predictor variables. One variable, I have age, foot length, shoe print length, and shoe size. Or I can use two variables, age and foot length, age and shoe print length, or age and shoe size, and so on. These are all the possibilities. If I look at stat, regression, multiple linear, I'm going to use that for everything because that way I can easily change it. My y variable is height because I'm predicting height. The first predictor variable would be age. I hit compute. There's my adjusted R squared, 0.1772, and my p-value, 0.004. This is a low R squared. We could do foot length. I'm not going to go through each one of these. I can do one with 2 to show you. I can go to options, edit, include foot length and shoe print. Hit compute. There's my adjusted R squared, 0.7484. My p-value is less than 0.0001. Why is it not best? It has a good adjusted R squared. This one is 3 variables, so it wouldn't be better. Shoe print, the adjusted R squared is low. Again, we're looking at R squared is less than 0.7014 for foot length, but we can eliminate this. Now we're going to look at two variables, and this has a higher adjusted R squared. Why is it not best? The adjusted R squared value is not much higher than 0.7014 for the single variable of foot length. Shoe print is probably more of an estimate of foot length because foot length is exact, whereas your shoe might be a little bigger than your foot, or it might be a lot bigger than your foot. This is not a very good model. Why would we use age? Even though it gives us a higher adjusted R squared, remember we said that the more variables, the higher the R squared, but not necessarily the better. Adding age when we already know that it's not going to help, but not necessarily the better. There are other cases using fewer variables with adjusted R squared that are not much smaller. Foot length is the best because it has a high adjusted R squared and a low p-value. And it's only one variable. Now, what's best may be different from what we should use. Application of regression methods would suggest that the best regression equation uses all four of the predictor variables because the combination yields the highest R squared value of 0.7585. However, given the objective of using evidence to estimate the height of a suspect, this is a great example of why critical thinking is so important. Let's do a little critical thinking before we look at the answer. If we're solving a crime and we're looking for evidence, even if age was a necessary predictor, what kind of evidence would I find in a room that would show me the age of a person? Age would not be even something I would want to consider if I'm trying to solve a crime, because I'm looking at evidence and I have no evidence of what age the person is. Foot length is great if the suspect is not wearing shoes, but that's not something that often happens. Even though that was the best equation, it might be harder to find that information. What would be a better one would be shoe print length because they're probably wearing shoes. And I don't really know what their shoe size or care what their shoe size is, but shoe print length is probably one of the best predictors because it is evidence that I will have. Solution. Delete the variables of age because criminals rarely leave evidence identifying their age. Delete the variable of shoe size because it's really a rounded form of foot length. And sometimes shoe sizes run differently. I'm sure you bought shoes and sometimes you might wear 8 and sometimes you might wear an 8.5. It's not a great predictor. Then we have, for the remaining variables of foot length and shoe print length, use only foot length because its adjusted R squared value of 0.7014 is greater than 0.6520 for shoe print length. And it is not very much less than the adjusted R squared value of 0.7484 for both foot length and shoe print length. In this case, it is better to use one predictor variable instead of two, because these are really similar and highly correlated. Although it appears that the use of the single variable of foot length is best, we also note that criminals usually wear shoes. Shoe print lengths are more likely to be found than foot lengths. That's our critical thinking skills, even though the actual foot length gives us a better predictor of height. It's much harder to get that kind of evidence, whereas we might find a shoe print. We've thought it through. We're going to use shoe print. Interpretation. Blind use of regression methods suggests that when estimating the height of a subject, we should use all of the available data by including all four predictor variables of age, foot length, shoe print length, and shoe size. But Other practical considerations suggest it is best to use the single predictor variable of foot length. The best regression equation appears to be height equals 64.1 plus 4.29 times the foot length. However, given that criminals usually wear shoes, it is best to use the single predictor of shoe print length. The best practical, so this is the best theoretical equation. The best practical regression equation appears to be height equals 80.9 plus 3.22 times the shoe print length. The p-value of 0 suggests that the regression equation yields a good model for estimating height. There is a very good example of being given a lot of information, but just using one piece of that.